That's a fun
Okay, guys, this is the top of the hour. Hope you're all doing okay. Survived. No big issues. Time to get back at it, yeah. Obviously, test not today. We need to finish up chair confirmations, material. I think the test should be on Monday.
Yes.
So we can get back into the groove of things. I don't like having tests on lab days. Busy with lab. Test on Monday. On this Friday, we'll begin test 2 material though. Unknown lab reports due in lab when you come to lab. I'll be returning the others during lab. We do have some quizzes to return. It's been a while. I'm trying to return these quickly, guys. If you'd like to pick it up here, you need to yell very loudly. If I don't hear you, you can't get it here. If you don't want to get it here, that's fine. Just don't say anything. Minna.
Here.
Brandon.
Here.
Camber.
Here.
Alexandra.
Here.
Karina.
Here.
No name. Rachna.
Here.
Sanjana. Sarah.
Here.
Sabatita. Ron. Here. Simone. Michael.
Here.
Jordan.
Here.
Allison.
Here.
Sinead. Rabia. Constantine. Here. Kendra.
Here.
Ty.
Here.
Emily. Daniel. Ryan. Oscar.
Here.
Layla. Kevin. Mattia. Hey, Terry. Sui. Charles. Stephen. Aaron. Michael. Aja. Tiffany. Lauren.
That makes me pretty happy.
Okay, guys. Okay, guys, let's get started. Thank you for your attention. In lab, we will meet downstairs. There's a video for the recrystallization technique. Any questions about lab this week? Any questions at all about anything before we get going?
Can we go over number 5 on Alkane?
Where are you at?
This one? Alkane.
Number 5?
Yes, sir.
Okay. I'll send that answer to you out. After you look at it, let me know if you have any questions. by email. I'll try to do that today. Alkane's warm-up.
And the acid base warm up.
For some reason, when you send out your emails, I'm not getting them when I was
Okay. I've heard a little bit of that. I'll see what's going on, and I think maybe the only thing you missed was I sent some warm-up keys. I'll send those again, including the one for the alkane, cycloalkanes. Is there something else? Okay, guys. We really need to look at this here. We looked at that during lab down here. Of course, you can have one substituent on a cyclohexane. If we had just one, that would be just methyl cyclohexane. We have two substituents. Now we have potential for isomers. Okay. We can have the two methyls in a 1,2 relationship and be a 1,2 isomer. It would be disubstituted. So this would be 1-methyl, 2-methyl cyclohexane. Actually, you would not call it separately. You would just say 1,2 dimethyl cyclohexane. Where this would be 1,3 dimethyl cyclohexane. And then that over there would be 1,4 dimethyl cyclohexane. So these are all different constitutional isomers. They have different connectivity and thus different names. Now, with the 1,2 isomers, or really any of them, but we also have the potential for stereoisomers. The two methyls can be cis. That is, they can both be projected the same direction. Cis. This is also cis. Here they're both projected back. Both being forward projection, dash one back. Tetrahedrocarbon. Two in the plane, one forward, one back. So these are cis. But then we can also have trans, where they're projected opposite. One forward, one back, or one back, one forward. So cis and trans. These two. One's cis, one's trans. They have the same exact name. Both of these are 1,2 dimethyl cyclohexane. Same exact name. So they're not constitutional isomers. Constitutional isomers have different names. Same name. If they're different, they're stereoisomers. And they only differ in some type of stereochemical descriptor in front of that same name. This would be called cis 1,2 dimethyl cyclohexane. This would be called trans 1,2 dimethyl cyclohexane. Now, as we'll learn down the road, these two are actually different compounds. They're both trans, but they are different. We'll learn more about that down the road. These two are actually the same exact compound. That can be confusing right now, but again, that's really test 2 material where we get more into stereochemistry. Once we do that, we can come back and look at this and say, okay, now do we understand why these are the same and these are different? That's in 2 or 3 weeks. So, the idea of constitutional isomers and then stereoisomers. Those are your two types of isomers. With stereoisomers, we'll see that there's some differentiation there. I think maybe we can get to the blue sheet. We need to get right into cyclohexanes. Okay, how do we draw this? Let's get right to it. Once we get through with sort of, the drawing and stuff, then we can fill in the miscellaneous blanks. Okay. Here's a cyclohexane. It's got one substituent on it. As we said, this thing cannot just rotate because we would break bonds and all this stuff. So it can't rotate like an alkane. What can it do? It can do what's called, first off, you have a boat conformation. We flip both ends up on the end. We know it's not planar, right? Benzene ring is planar. We talked about that. This is all tetrahedral, so it leads to this sort of non-planar, a little bit more to it. Both ends up, that's called a boat conformation, like the Italian gondola. That's not good because groups up here will interact. And that's the last we'll say about boat. Typically, one end will be bent down or away. That's called a chair. You can sit up here and your feet can spill over. Now, this thing can interconvert between two different chairs. For example, this can come up and this can come down. That leads to another chair. That's just where the feet are hanging over this way. Up, down. And this is your so-called conformations, or your rotomers. It's not really rotating, but interconverting between conformations. And there's also some in-betweens, and sometimes books will talk about it. I'm not really going to talk about it. We're either going to look at this chair or this chair. Now we need to know how to show this on the board. Also, we need to be aware of what happens to substituents. If we look at this chair conformation, this group here is going to be called axial. We'll draw this on the board. But when we do a ring flip, pull this up and pull this down, this group is now equatorial. We need to be able to keep track of where groups are when we do this. Also, if we have multiple groups, we talked about cis or trans. We also need to be able to recognize cis or trans in this type of drawing, when it's shown like this. Because we can draw it on the board like this and maybe say, okay, we have a chlorine here and a chlorine here. And those two are easily known to be cis. But what if we draw it in chair conformation? Can you recognize cis there? Okay, how do you draw these? We did this. I'll try to do it here. I'll probably make a little more space. Two lines, a little bit offset, like this. That's actually 4 carbons. We can connect the ends. Now we got 5 carbons on the board. And then we can come here and connect here. It will take you a couple of times to get it reasonably. There you go, there's a chair. You sit here, and your back is here, and your head, your feet spill over. I'm a terrible drawer. Not even going to try. That's a chair conformation. But what about H's? You need to be able to draw in the substituents on the carbon. This is a carbon. It's got 2 H's. If we just consider cyclohexane. Okay. We're going to have up and down H's. This is an up carbon. This is an up carbon. This is an up carbon. I wish my model was 5 times bigger. I just don't make large models for this type of thing. But this is an up carbon, up carbon, up carbon. If you kind of have it, I don't know if we set it down. I know many of you can't see this. But these 3 carbons are sort of just higher. Boom, boom, and boom. These get straight up hydrogen, or straight up bonds. Now, this bond is supposed to be meant to be a little bit in front of that one in the back, but we're not showing any boldness or anything. But it's on the board like supposed to be on the board like this. So this is in front of that back there. This H here, you can either draw it a little short and draw it like that, or we could have drawn it a little longer maybe. Let's see what looks better. In any event, the straight up carbons get straight up bonds. If we draw it a little longer, something like this, but this bond is in front out here, behind that back bond, yep. Okay, the 3 down carbons get straight down bonds. Straight down. Straight down. Again, you can draw that sort of short or a little bit longer, straight down. There's half the H's. 6 of them. We got 6 more to put up here. These are your axial H's. They're straight up or straight down. Okay, the others are a little bit more trickier, although if you see what's going on, it's not tricky at all. It's going to be an H. It's going to go to the outside. Let's look at it. By the way, if we set this guy, can everybody see that chair? I don't know if you can see this or not, but there's the head. We set this down. How many H's are on the table? Straight down. How many H's are on the table?
3.
3. Those are the 3 that are straight down we drew. Okay? We turn it over. How many are on the table?
3.
Those are the 3 that were straight up when we turned it, okay? 3 up, 3 down. The other 6 never hit the table. The other 6 are to the side. Or really, we're going to call them equatorial. Equator. Like the equator going around the Earth. Those never hit the table. Those, we draw those, it's going to be here. Because we look at it, here's this one straight up, but then there's one here. Okay, equatorial. Now how do you draw it? It is going to be parallel, not to the carbon-carbon bond it's attached to, but the next one. So that is parallel to either one of these. Boom. And so this is equatorial. This one here, parallel not to the bond here, but to the next one. So it's going to be parallel to this. This one, not parallel to that one, not the one it connected to, the carbon-carbon bond there, but the next one, here. This and this are parallel. This one. That and that parallel. That one, can you draw that one in? Parallel not to that one, but this one. And sometimes, depending on how your ring is, sometimes this can be a little skewed, and you're like, well, if I draw it parallel, that's going to make this uglier. Back here, sort of like that. We have all 12 hydrogens now drawn in. Yeah? And that's a nice cyclohexane in a chair conformation. Now let's star this hydrogen here. Let's keep track of it. We're going to do a ring flip is what it's called. A ring flip is where we go and we're going to pull this end down and this end up. That leads to another chair conformation. Okay. Let's pull this end down and let's pull this end up. Let's do this. Let's call this H over here R. And then we can define R in a little bit. R can be some variable substituent, usually a carbon substituent. Okay, so pull this down. How do you draw it? We started this one by drawing what? Two like this, and then that's how we got to this. To draw the other one, we're going to do the same thing, but we're going to draw these like that. And we're going to connect these like this and like that. And that would be better to be a point, but it's close enough. Because this end, this here we're pulling down, and this up. So now that's up and that's down. We put in our H's real quick. That's an up carbon, gets you straight up. That's an up carbon, straight up. That's an up carbon, straight up. Down carbon, down carbon, down carbon. This is going to be boom. Maybe not so long. What do we got here? Yeah, this is kind of a bad bond angle because that's kind of fat, but that's supposed to be parallel to this, yeah. This here, that's supposed to be parallel to what happened there. Parallel to that carbon bond. Close enough. Certainly it's supposed to be equatorial. So that's where this ends down and this ends up. Where's this H at now? The one that we starred. Which one is that H?
Equatorial.
Which one is that?
That one right there.
This one right here. That one right there. That H is up. Pull that down, push this up. This model should be a lot bigger. Okay. But it's now there. Here's the take home. Very important. Whenever you do a so-called ring flip between one chair to the other chair, all of your axials go equatorial, and all your equatorials go axial. Where's the R group at? Where's the R group at? If we were to erase an H and replace it with R, which one?
The topmost on the left, that one.
This one here. It's equatorial here, but now it's axial. Okay? We just call this the R group. Take it off and put it here. That's supposed to be that on the board. R group is equatorial. There's your down axial. We flip this up, flip this down. But now the R group is straight up. Simply put, when we do a ring flip, the equatorial went axial. Okay, these are known to be in equilibrium. That is, this can flip back and forth. Okay. These are the two main ones to consider. Which is favored? Well, if it's all H's, they're both the same, and it's not even valid to ask which is favored. What if it's an R group? I'll kind of write here. Hopefully you have a little room. If R the R group equals methyl, that is a CH3, the ratio of these two is 18 to 1. So which is favored? R group being equatorial. 18 times. Now that should make sense. Or why does that make sense? Or that's the take home. Groups have more room equatorial. Okay? It's best for your largest groups to be equatorial. When they're equatorial, they're out here and you actually have more room. Okay? I can see that better by comparing it to axial. When they're axial, the main interactions that you get, which are bad, is the interaction between this axial group and the other two axial groups, even if they're hydrogens. This is called 1,3 because that's carbon 1, 2, 3. 1,3 diaxial interactions. Your 1,3 diaxial interactions are not good. It's big groups, which largely have electrons on the exterior, interacting with each other. When this thing pulls down and it goes up, this is a wave. Yes, there's things here, but this is not sticking up like this. It's away and there's just more room. You can look at models and see more room. You can see maybe space-filling models. The take-home is, what's the preferred position? Equatorial is your preferred position for your bigger groups. Preferred position, 18 to 1 when it's a methyl. What if it's a larger T-butyl? I did. What if it's a larger T-butyl? Which of course is carbon with 3 methyls, right? This guy really wants to be equatorial because it's even bigger. It's even more sterically demanding. And the ratio there is known to be 4,800 to 1. So you go to an even bigger group, it's way much more demanding and it's going to be preferred there. So equilibrium is like almost like it's, you with me here? Even more demanding. That's just a couple of examples. Now some folks will go into quantifying this, giving this a steric value. I'm not going to get into that. Just like we did with rotamers. Bigger alkyls are going to be more demanding. Bigger halogen, more demanding. Okay? Let me ask you this question. As drawn on the board, the starred H and the R group. First off, what's their relationship? Is it 1,2, 1,3, 1,4, 1,5? No such thing as 1,5.
1,4.
It's a 1,4 relationship, right? Because if this is 1, then that over there would be 2, 3, 4. So the previous page, we looked at 1, okay, that's a 1,4 relationship. Pretty straightforward, yeah? Question. Is the R and the H group that stars cis or trans? Cis or trans? How about here, cis or trans? Cis, very easy here. But guess what? The ring ain't really flat. So this is not a super informative representation, although we draw these like these all the time. We know it's really very 3D, tetrahedral carbons. Cis or trans? They are cis. Okay? Two star groups are cis. How do we know they're cis? By the way, when we do a ring flip, what are they now? We're saying they're cis. Let's draw cis here, or build a cis. Cis 1,4. If this ring was flat, Okay, I tried to make it flat. Okay, the two reds are which way? Are they projected the same way?
Yes.
Yes, they're cis. But we know the ring ain't flat. You see what happens when you make it flat? I broke my bond. All right, let's go back to tetrahedral. Okay. Now what? Let's try to get a boat. Not a boat, a chair. Okay. These are cis, right? I didn't disconnect anything. They're cis. Okay. That's it. What is it over there? We label this cis. What is it over here? Cis? Anybody else? What is it on the right?
You want us to say trans?
Nobody wants to say trans? Why not? Why is it not trans over there?
It's not changing connectivity.
The only way for it to be trans is for me to take this off and reconnect it here. They're not trans. They're both cis. Don't fall into the trap just because of the ring flip. Yes, equatorial went to axial, but cis is still cis. It's the same compound. We just did a conformation rule, okay? It's still cis. How do you look at these and tell they're cis? It's because, here we go. If you look at the two things on the carbon, the R group is up, the H is down. So it's up. Up compared to the other thing. Well, what about this star at H? How is it compared to the other thing? It's up. They're both up. It's cis. What about over here? How's the R group compared to the other thing? It's up. What about over here? How's the H compared to the other thing? Up. It's cis. Now, yes, over here they're both axial, and over there they're both equatorial, but that doesn't have anything to do with them being cis. Okay, H1 and H2. Are these cis or trans? They're trans. Maybe this is easy. The H is down compared to the other thing, right? It's down. And this is what compared to the other thing? Up. They're opposite. They're trans. Okay? And if I drew this compound in a perspective drawing like this, and I wanted to draw them trans, I would draw one like this, and the other, we got to be careful over here because we could get into mirror images, but this would be trans, right? Trans 1, 2. Well, this is also trans 1, 2. You got to be able to see it in both. Okay, let's see what we can do here. Already got it there. Cis or trans? Now, we don't have to always draw in the H's. Usually, if you're doing something officially, I want you to draw in the H's, all the bonds. But in these drawings, the H's aren't drawn in. First one, is that cis or trans? Well, if we drew in the H, how would it be projected here? Yes, very good. This one? Yes, very good. Okay, the chlorine is down compared to the H, the bromine is up compared to the H, these are trans. How about those two?
Cis.
That's a downer, that's a downer, they're both up compared to the H's, that's cis. How about this guy?
Trans.
Trans. This trans, they're both equatorial. This trans, one's equatorial, one's axial.
Chlorine is bigger than fluorine.
Do what?
Is it because chlorine is bigger than fluorine? And it's more stable?
We need to talk about that, yes. Is that the best conformation? We'll do some below. Show this as a perspective drawing. Perspective is where you use dashed and bold. When we do chair conformations, you do not use dashed and bold because the projection is built in. Well, just the way it is, you don't need dashed or bold. The projections are implied just the way the ring is drawn. But in a so-called perspective, this would be a perspective. So, do we have a cyclohexane? Six-membered ring? I see a six-membered ring. I've got a bromine, a fluorine, and what's this group? Isopropyl. Okay. Okay, I'm going to put the isopropyl here, and I'm going to do it back. Okay. So where's the fluorine at? It's next door. If that's one, fluorine's on the two. I'm going to put the fluorine here, and I'll tell you why here and not here, maybe. Okay, do I want to draw it dashed or bold? Yes, dashed. Okay, where's the bromine going? Finish it up. Where's the bromine go? Right here?
Yeah.
And it will be bolded. Now if I took this and made a model of this and held it up there just like this, I could then turn it and make sure it's in a chair conformation, and then it should look just like that. Any other answers here that you may have gotten?
Two dash, two bold and one dash.
Two bold and one dash. Bold, and dashed here. Let's compare that. Bold here. These have the same relative configuration. That is, these are cis, those are cis. These are trans, these are trans. Problem is, I think this is a mirror image. Just like if we were drawing hands on the board and this was this one, then you drew this one on the board. Yes, the thumb is right next to the pointy finger in both of them, but it's just the mirror image. We'll talk about that later. The way I was doing it to avoid drawing the mirror image is I was pretending I was up here, sort of hovering and looking down. And this was sort of the board there. And if I'm up here, the isopropyl is going away from me. You see that view? So that's why I drew it going away from me. If the isopropyl is going away, well then the fluorine had to be going away. Why did I put it on the left? Because look up there. If I'm up there hovering, this carbon here, this bond is more towards you guys. So if I'm hovering, it's on my left. So I was kind of seeing that. And then the bromine is down here, but see how the bromine is coming towards my feet? That's why it's bold, it's coming towards me. So I was kind of looking at it. If you were to do this, I would give you a whole lot of credit and maybe full credit because we haven't really seen, we haven't gotten into this far. Common mistake here is just drawing this bold as well when they're cis here, but they ain't cis there. Another common mistake is to boom, boom, and put the bromine here. And then it's like, well, that's 1, 2, 3, but up here it's 1, 2, 4. So you got to know where things are connected. That's your connectivity, but also your projections. Other questions here? Let's do one at the bottom. Show the following in the lowest energy conformation. How many groups are equatorial in the best conformation? Yes, large groups prefer equatorial. But does that mean that they're all going to be equatorial? No. There's some compounds where you can't have them all because they're in a certain orientation to each other and only maybe one can be equatorial. Question?
I was just confused as to which bond you run parallel with the hydrogens when you're doing the ring. So like on the perspective drawing example we did, off the fluorine, which way would that hydrogen run?
Where's that at? Here?
It's way up on the right. It was what we were talking about earlier. I'm sorry.
The ones that were drawn without hydrogens?
Yeah, so under the show as perspective drawing.
This is an up carbon. Up carbons get up H's.
Right.
The one on the right.
The one on the right. Where
Which one?
the fluorine,
The far right.
the far right. So the H off of that one, where would that go? It would be run parallel to the.
Oh, the fluorine?
Yeah. Yes, the H off of that one.
It would be parallel not to the connected bond, but to this one.
That's okay. It would go to the front. Okay.
That's a down.
Uh-huh.
So the other one can't be down. The other one is equatorial. Because that's down is axial. The other thing here is equatorial.
Okay.
That's equatorial. The other thing is axial.
Okay.
That's an up carbon. It gets an up H. That bromine is in what position?
Oh,
Equatorial. So the other thing is axial. And that makes sense because that's a down carbon that gets a down bond. Let's look at the bottom. Draw these in the best conformation. Compound here. Draw it in the best conformation. What's the best conformation?
With the bromine
Largest groups,
down.
equatorial. Here we go. Boop, 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 boop. This is a little short, maybe. Boop, boop. Yeah? Okay, there's different ways to do this. I'll show you how I do it. What's the biggest group here? Bromine. Let's make sure at least one of the bromines is equatorial. Better both of them. But we may not be able to do both of them. I'm not going to worry about mirror image. Like I told you earlier, I'm not going to worry about it unless I see it's easy to do. We'll do more of that later. Or we may come back after we finish and say, okay, is that really the mirror image? Here's how I do it. All right, I got bromines. I'm going to put one equatorial. Boom. There we go. All right. Could I put it here, here? It don't matter. Put one there. Now it matters because now the next one goes where? Next door. It's 1, 2. Well, let's say this is next door. If that one's there, how do we draw the next one? Axial or equatorial? It's going to be axial. Because these two bromines are cis, correct? They got to be cis here. We're drawing the same compound. If that one's equatorial, and this one's cis, 1, 2, it has to be axial. Here's the answer. They both cannot be equatorial. Right, but they wouldn't be cis. If they were trans, they could both be equatorial. But it ain't trans, it's cis. So the best we can do is have only one equatorial. But which one? Now we've got a fluorine, and if this is 1, 2, 3, and that's 1, 2, and the fluorine is here, correct? How should we draw it? Axial or equatorial? It's trans to the bromine, so that means it's going to be axial, correct? Because aren't these trans? Yes. So what do we have here? Is that the best we can do? we've got actually two axial and only one equatorial. What if we do a ring flip? What would we have? These would go equatorial, and that would be axial. Would that be better? Yes. In both conformations, you've got one, these are one's one way and one's the other. So make sure this is equatorial. And if you do a ring flip, now how do you do a ring flip? You can pull this down and pull this up like we did earlier. Or you could do it like this. You could come back and say, you know what? I always like drawing them like this. But instead of putting it together like that, I'm going to make the first bromine axial. I'm just going to kind of redo that. And if that was axial, how is this one? Equatorial. And this one is what? Equatorial. Now it's kind of skewed here. This could be a little bit, but this is supposed to be equatorial. Now usually I want you to draw in H's that are on the carbons where your substituents are. If we're doing the H here, it would be like this. This would be what? Straight down? And this would be what? The H. Straight up? This is actually a ring flip. The problem is it may be a mirror image. But I'm not going to worry about that because guess what? This may have been a mirror image if we didn't consider it correctly. We're just not ready to deal with that quite yet. So these may be mirror image of themselves, but it's okay at this point. Okay. Are the bromines here cis?
Yep.
Yes, like they're supposed to be. Is this bromine in the fluorine trans? Yes. In this conformation we have equatorial, equatorial, and axial. Is that better than axial, axial, equatorial? Where in both, one bromine is equatorial. You see, the bromines are a wash. Because here's one's equatorial, here's one's axial. There one's equatorial, one's axial. So we let the fluorine went out and put it also equatorial. This is your better one. Questions? Again, I did not do a ring flip. If you want to do a ring flip, you can do that. And you draw it like this real quick. Boom, 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 boom. The bromine would then be where? Bromine 1. Bromine 1 would be here. This carbon is actually now here. And it would be, well, that's an up. It would be like this. And the fluorine would be here. And that's a downer. But it would be like this. Axial to equatorial, axial to equatorial, equatorial to axial. And this one should match that one over there because you've got one bromine each way and fluorine is equatorial. But they may be mirror images, just for the record. Don't worry about that. Question?
So it really doesn't matter which one you start with, right?
Doesn't matter which one. I started with the bromine here, then the next one goes here because the bromines are 1, 2. Right? That's the way I do it.
But you go around, like what is opposite, I guess?
Well, 1, 2. I could have put the second bromine there and moved
Yeah,
it 1,
so
2.
it doesn't matter as long as it's next.
Well, again, you may have ended up with a mirror image, which we're not worried about. Question?
For the ring flip one, is it okay for the first bromine, do it equatorial up and the second bromine axial up?
Tell me again.
For the ring flip one, could you have drawn the first bromine equatorial and the second one axial?
Not if it's an exact ring flip of this, because when you ring flip, the bromine equatorial is going to go axial. That's an exact ring flip. Pull this down, pull this up. When you do a ring flip, everything switches position in terms of axial equatorial. You started this carbon, that carbon is now down here. We pulled it down. But again, I got the answer by just redrawing it and switching everything. Okay, there's others to work. We're out of time. Let's see. We got one to work over here. There's a couple that we didn't touch on. Nomenclature there. You've got the warm-up page at the beginning. We'll see what type of questions there are the first 5 or 10 minutes on Friday.